Hello everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. Today's session we are going to see the transformation of random variable and we will be solving some real-time problems on transformation of random variables. At the end of this particular session, so we will be learning two learning outcomes. One learning outcome is what is the definition of transformation of random variable? Why do we need transformation? What is the need of transformation? So different classifications of transformations, and later on we will apply these concepts for solving the real-time problems. So what is meant by transformation of a random variable? So transformation of random variable means deriving the distribution of new random variable function defined for another random variable. So let us take two random variables x and y. When we do the operation on random variable x, we will get a new random variable y. So we can do different types of operations. In general, the operations are monotonic transformation. Monotonic transformation means it is classified into two types: monotonically increasing function, monotonically decreasing function. That in the sense, if x is increasing, y is also increasing correspondingly, we call it as monotonically increasing transformation. If x is decreasing, y is also decreasing correspondingly, then we call monotonically decreasing transformation. And non-monotonic transformation, if x is increasing, y is not decreasing, or if x is reducing, y is increasing. So in such case we call it as non-monotonic transformation. So in general we apply transformation for, and we want to change the random variable or we want to apply any operation on a random variable, it is going to generate a new random variable. So that new random variable is called transformed random variable. So see here, we can see here x is a random variable which is applied as an input to the function. When we apply some function, the function can be of any type function. So the output of this function gives you the new random variable y. So let us assume the distribution function and density function of input random variable x as fx of x and small fx of x. The corresponding outputs what we will get as y, the y related distribution function and density function. So in practical scenarios we will apply these concepts. We need to transform one random variable to another random variable, or we generally express one random variable in terms of another random variable. For example, when we are comparing, let us say mileage of a car, let us say mileage of a car, one is some described with a random variable x, another car is there, that mileage is also described with a random variable y. Assume the second car is providing twice good mileage when compared with the first car. So we can relate how y is equal to 2x, provided x is a random variable which describes the mileage of a car. So second car is giving you good mileage when compared with the first car. So you can relate y is equal to 2x. Clearly here 2 is the operation we perform. 2 is nothing but operation. Here 2 is nothing but scaling, scalar. It is a scalar which scales the x. That scale value is equal to y. So in general scenario, we also apply the transformations on a random variable. This is scaling is also a transformation, amplification you can say. So we also apply different types of transformations. One by one we will see. A monotonic transformation. Monotonic transformation is two types: monotonically increasing transformation, monotonically decreasing transformation. Monotonically increasing means as x is increasing and y is correspondingly increasing, we call it as monotonically increasing function. If x is increasing, y is decreasing, then we call it as, if x is decreasing, y is also correspondingly decreasing, we call it as monotonically decreasing transformation. So whenever the function is monotonically increasing or monotonically decreasing, there is a relationship between the distribution functions and density function. Distribution function fi of x, y is equal to fx of x, whereas density function, this is more important, density function of newly formed random variable is equal to dx by dy into fx of x. Similarly, for a monotonically decreasing function, fi of y is equal to fx of x into minus of dx by dy. So in general, whether it is a monotonically increasing or monotonically decreasing transformation, in general we can express the output random variable density function is equal to fx of x into absolute value of dx by dy. So, this is the general relation for conversion. And similarly for a discrete random variable also we can apply these concepts, not only for continuous random variable. So, let us see one problem related to the discrete random variable, how the relation will, how the transformation will change the output random variable values. See here, x is the random variable given its probabilities. Now, there is a function which relates the y and x, this is nothing but transformation. Now, y is equal to x square. So, y is equal to x square, the probabilities remain same, whereas because of the transformation the y value will be x square, 2 square, 3 square. Now, we can compute the probability corresponding distribution and density function. Here you can clearly see the distribution of y is directly obtained by squaring the values and transferring the probabilities. So, this is how we apply for a discrete random variable. Now, we see one problem related to the continuous random variable. It is a monotonic transformation, y is equal to some ax plus b. So, it is a linear transformation. So, linear transformation y is equal to ax plus b. So, y is nothing but transformation of x which is equal to ax plus b. From this x is equal to y minus b by a, x is equal to y minus b by a. From this we know dx by dy is equal to 1 by a. Now, we know the relationship between y and x in terms of density function, fy of y is equal to absolute value of dx by dy into fx of x. Applying this, dx by dy is 1 by a, fx of x is fx of x simply. X can be replaced as 1 by a, fx of y minus b by a, y minus b by a. So, like this we can apply the formula for computing the problems, density function formula. So, let us check for a Gaussian random variable. So, we need to prove that the linear transformation of a Gaussian random variable is also going to produce another Gaussian random variable. The transformation linear we can use the same which we used earlier, y is equal to ax plus b. Applying that, so the density function of random variable x is given as fx of x is equal to 1 by root 2 pi sigma x square e power minus of x minus mu x whole square by 2 sigma x square. Now, the newly formed random variable density function is equal to absolute value of dx by dy into fx of x. So, absolute value of dx by dy is 1 by a, fx of x I replaced with general equation. We know that x is equal to y minus b by a, I replaced with that. After doing the LCM, y minus a mu x plus b whole square by 2a square sigma x square. Here we can assume mu y is equal to a mu x plus b and sigma y square is equal to a square into sigma x square. Let me do this thing. What happens? This function will reduce like again a Gaussian function. So, linear transformation of a Gaussian random variable is going to produce this another Gaussian random variable with the mean and variance with a different value. They can be interrelated with the existing random variable mean and variance like this. Okay. Another one is non-monotonic transformation. Already we have seen that sometimes if x increases, y decreases, sometimes if x decreases, y increases. So, in this scenario, this transformation we call it as non-monotonically transformation. It is not strictly increasing or strictly decreasing random variable. Sometimes it is increasing, sometimes it is reducing. So, for a non-monotonic transformation, let us see one problem. Y is equal to x square is an example of a non-monotonic transformation. Y is equal to x square represents a parabola. Clearly, it is a non-monotonic transformation. Let us apply this one. We know that fx of x is given and it is defined over the range minus 1 to 3. the transformation is y is equal to x square. From this dx by dy is equal to 1 by 2 y power minus 3 by 2, that means 1 by y power 1 by 2 whole power 1 by 2 root y. So, when you do the differentiation dx by dy will be this. Now, y is equal to x square, x limits are from minus 1 to 3, y limits will be 1 to 9 because of this function transformation. Now, the PDF of the newly formed random variable fy of y is equal to, what is the density function given to us? 1 by 4. So, dx by dy into fx of x, if it is the case for monotonic transformation. For a non-monotonic transformation, we generally do not apply like this. For a non-monotonic transformation, the formula is fx of x, absolute value of dx by dy, like this we will apply. So, applying that, the slope is 1 by 4, 2x, x is equal to minus root 5, I am substituting for one function, x is equal to root y, I am substituting. Totally, I will get fy of y is equal to 1 by 4 root 5, and the y limits are also changed. Okay. Next, given x is a uniformly distributed function, we know the uniform distribution function fx of x is equal to 1 by b minus a less than x less than b. Applying that concept, minus pi by 2 is a plus pi by 2 is b. Applying that 1 by b minus a, we will get the uniform density function as 1 by pi over the limits minus pi by 2 to plus pi by 2. Now, the transformation here applied is a non-linear transformation, y is equal to tan x, it is a non-monotonic transformation. So, now dy by dx, dy by dx is equal to secant square x dy by dx. When x is equal to minus pi by 2, y will be minus infinity. When x is equal to plus pi by 2, y will be infinity. So, the limits of y are changed, and this is the transformation t dash of x is equal to secant square. So, fy of y is equal to fx of x divided by transformation 1 by pi secant square x, and x values are tan inverse y. So, substituting this, we will get fy of y as 1 by pi 1 plus y square, and y limits are now minus infinity to plus infinity. And this is another problem which is related to monotonic transformation. Monotonic transformation, given it is a uniform random variable. Uniform random variable, this is a, this is b, this is 1 by b minus a. And the range is given 0 to 1, 3 to 5. So, when range is from 0 to 1, y will become, based on the relation 2x plus 3, the y range will be 3 to 5, and dy by dx or dx by dy is 1 by 2, x is equal to y minus. So, now the PDF is fy of y is equal to absolute value of dx by dy into fx of x. Using this relation, we can write it as fy of y is equal to 1 by 2 over the range 3 to 5. For the computed or for the newly formed density function, we need to compute the mean value and variance. So, the mean value, expectation of x 1 by 2, expectation of, variance of x is given as 1 by 12. Are they given? No, we need to compute them. We need to compute, we know that for a uniform function, uniform density function, it is a plus b by 2. A comma b is equal to 0 comma 1. So, the mean value is 0 plus 1 by 2, you will get 1 by 2, and variance is b minus a whole square by 12. So, the variance of uniform function 1 minus 0 whole square by 12, we will get 1 by 12. Now, the transformation is given as y is equal to 2x plus 3. So the now new mean value E of y is equal to 2 into E of x plus 3 and variance of y is equal to 2 square into variance of x. Variance of constant is 0. So like this, with the help of transformation we can compute the new statistical parameters for the transformed random variable. So in this session what we have seen is, what is the need of transformation in many practical scenarios where we need to transform one random variable to another random variable, and also we have seen the different transformations that are possible. Monotonic, in monotonic increasing, monotonic decreasing, and another transformation is non-monotonic transformation. And we have seen the transformations for both continuous and discrete random variables. Later on we have seen some practical problems, real-time problems, where we should apply the transformation concept so that the newly formed random variable parameters calculation, like statistical parameters like mean, variance, and computing the newly formed density function we have seen. So in the next class what we will do is we will extend the operations on random variables to the multiple random variables. Multiple random variables, mostly we will be seeing two-dimensional random variables. We will apply the operations on multiple random variables. Thank you.